back on the light board. Hope this is going to work. So we've got only 2 or 3 lectures left. Well, officially 3 lectures. I might do only 2, we will see. I want to spend this lecture talking to you more about Markov chains. As I introduced the other day, Markov chains are these very cool tools to study stochastic processes, so processes that change with time, that evolve with time in a stochastic manner, in a random manner. So this is, we stopped 1 slide after that the other day, but I believe it's worth going back into this. Recall, I'll sort of caricature what we have. We have a number of states where it is potentially possible to move between those states. We have R of n. We don't know exactly what's happening. You might be able to go back and forth. You might stay in some of those states. This is the general idea. So, as I pointed out the other day, so what we do is we consider a vector, later a vector, but for now we first consider this pi here to be the probability that the state is in one of the system is in one of those states at a given instant in time. And this is a probabilistic point of view. We could have, if I want to be sure that my system is in a given state at a given instant in time, I could, for instance, say that P1 of n equals 1. If I say that, what I'm saying is that with probability 1, the system is in state 1 at time n. Okay? But in practice, we don't necessarily know. And one of the things we use Markov chains for is to try to determine what the probability is that we are in some of the states. Okay, we're not necessarily interested, and I'll show you actually in numerics later how you can use Markov chains for both purposes. You can simulate a process that is jumping from one state to another, but you can also think about describing the mean state of the process. And as I said, I'll show you an example later. So we define those numbers, and I'm going to erase this one because this one is a really particular case. We define the number, the probability pi of n that a state is in, that the system is in state I at the nth repetition of the experiment, that is the nth time step. Remember what I stressed quite a few times, the system has to be somewhere. We don't allow the system to be unknown. So that means that the sum of those probabilities of being somewhere needs to be 1. Okay, the sum, the complete state space has to be occupied. The system has to be somewhere. So we have this relationship here. And now what we're doing is we look at the probability that the system got somewhere, so state I, at the n plus 1 time step. Okay? And it could have come here. So suppose this is state I. It can have come here from any of the other states. So it can come from S1, it could come from S2, and so on and so forth. It could actually also come from itself. But it has to come from somewhere. So first thing that could happen, it was in state 1 at time n, and it switched to here at time n plus 1. Then the probability, remember how we define this, the probability of switching from 1 into I is what we denoted pi1 here. 1i, sorry, probability of moving from 1 to I. But seeing how we define this, the probability that the system was in state 1 before it made this transition is P1 of n. So the probability that it switches into state 1, given that it was state I, given that it was in state 1, is this product here, P1i, the probability of making this transition, times the probability that it was there. And so on and so forth. The probability of moving from 2 into I is the probability that I was in 2 and that I moved into I. And so on and so forth. And this is so what gave us in the last lecture the fact that the probability of being in state I at time n plus 1, there's a lot of letters involved, so it's easy to make mistakes. So the probability to be in state I at time n plus 1 is the probability that I was in state 1 and I transitioned into state I, or, so plus, the probability that I was in state 2 and I transitioned into state 1, or all the way to I was in state R, the last of one of the states, and I transitioned into state I. Okay, so when I write this up, and I need to write it up for every single possible state, I get that the probability that I'm in state 1 is given by this equation, all the way to the probability that I'm in state R is given by this equation. So if you look at this equation, it uses indices not the way we have used them so far. If you look, I'm going to put P1, P2, all the way to PR as a vector, and I don't know yet how I'm going to do it, okay? Whether I'm doing it in row or in columns. And then if you look at this, so if you remember when we were looking at classic linear systems, we had something like this. So if we had a matrix A11, A12 to A1n down to AN1, ANN, so a square matrix, and I multiplied this on the right by x1 to xn, what I get in my first row is A11 x1 plus A12 x2 plus A1n xn, oops, down to AN1 x1 plus ANN xn. Okay? Compare that with those equations here. Here I have 1, 1, P1, so this would match what we have here. But here I have P21 times P2. And here I have 1, 2. So I can think of 1, 2, 2, 1 there is the transposition of P. Okay? I can think of, if I took this, if I call this A, I could take A transpose X. When I take A transpose X here, I get A11 X1 plus A21 X2, etc. So this could be P transpose. But another way to do it, which doesn't involve the transpose, is to left multiply by a row vector, which amounts to the same thing. Okay? It's just the same way as writing the transpose. Okay, think about it. So because when I transpose, so if X is a row vector, a column vector, and I'm multiplying this by a transpose, this is the same as if I transpose all this, I get the transpose of this times A. Okay, when I transpose all this. And this is what we're going to do. So in this vector here, this is complicated to do, in this vector here, we're therefore going to assume that the vector of probabilities to be in a state, so P1 of n, P2 of n, etc., is a row vector, and that we're left multiplying the matrix P, the transition matrix. Let me see if I can do this. Oh, nice. Okay, so you see what I'm doing. I'm taking P to be a row vector, and I'm multiplying the matrix by this row vector. So when I do the computation, I get this entry times this one, plus this entry times this one, plus this entry times this one, etc. This is, so the result is a row vector, where I get the product of the vector times the first column, the vector times the second column, the vector times the third column, and so on and so forth. Okay, so this is not what we did up to now, and it is completely possible to write the system the other way. Okay, instead of writing that Pij is the probability that I'm going to state J given that I was in state I, if I had written that this was the probability of going to state I given I'm in state J, then I could have used a column vector on the right and the matrix P on the left. It just makes more sense to me to think about the P, the transition matrix, as representing in rows where you're coming from and in columns where you're going. It's just a convention, and some textbooks will be using what we're doing here, and other textbooks will be using the other notation. Just read into the definition of the terms. Just check whether the author is using this for Pij or this for Pij. Okay. So what's important is we can write this evolution of the probability vectors as a it's actually a system. Okay, it's a sequence. So what that expression that you have here, that I had highlighted and that I sort of erased the highlighting for, it defines a sequence. Okay, you've seen sequences probably of scalars where you had something like this. Let me finish erasing. You had something like this where x, let's say t, was a real number, and then you said something like x of t plus 1 was equal to axt. Okay, where a is also a real number. And you initiated this sequence with some value x0, and then got from this that x1 was a times x0, x2 was a times x1, but x1 is a times x0, so that was a squared times x0, and so on and so forth. Well, this is the same thing. This here is exactly the same thing, except that on the left I have a vector, on the right I have a vector times a matrix. But the ideas are exactly the same, and what we do with this sequence or this sequence is the same. Okay. So we call So this is a Markov chain with transition matrix P and capital P, okay? So that's called the transition matrix. And the vector P, the row vector in this case, the row vector P is a probability vector. So it sums to 1. So let's think about this equation, and let's see how we can make it talk, and so to speak. Oh, I have my chair overlay. So this brings us back to one thing that we have already seen. Okay, so these are stochastic matrices, and I'm giving you the definition again, and we're going to see again the same type of thing we've seen before, because it's useful to go over these concepts again. So I'll very briefly remind you that a non-negative matrix has to be non-negative, so all these entries are positive, are non-negative, is called stochastic. Here the definition is by row, okay? I'm summing from J is 1 to R of the aij's, so this is a row stochastic matrix. Each row sums to 1. If a column sum to 1, we talk about a column stochastic matrix. Often we don't say which side, because of course if you transpose a row stochastic matrix, you get a column stochastic matrix and vice versa. But so if you have just a stochastic matrix, it typically means that only one of the directions sums to 1. Otherwise it's called doubly stochastic. And these have additional properties that we're not going to look at. Another thing that we already talked about is the fact that if we have a stochastic matrix, then we can show easily that all eigenvalues of that matrix are less than or equal to 1 in modulus. And furthermore, remember that was an exercise we saw before, furthermore, 1 is an eigenvalue. And 1, remember, in that case, ends up being called, well, it's the spectral radius of the matrix, and it is an eigenvalue. Now, we can say a bit more, for instance, if the matrix is irreducible. And this is also something we have seen before, but now that we've done graphs, I want to bring you back to this notion. So a matrix is irreducible if we can find, we'll start with reducible, not irreducible. So a matrix is reducible if I can find a permutation matrix, that's a matrix of zeros and ones that just reorders the rows and the columns of the matrix. So we can find a permutation matrix P and some number R that is between 1 and n, okay, n being the order of the matrix, so that the matrix can be written in block upper triangular form. Okay, the block, the top left block, has R is R by R, and the top of the bottom right block has dimension n minus R. Okay, that means this one has R rows. It has as many rows as A11, and n minus R columns because it has as many columns as A22. But it doesn't matter what this one does or the 0 here does. What's important is those two guys. Okay? If it is not possible to put the matrix in this form, we say that the matrix is irreducible. And one thing that I already emphasized, and I will emphasize again, is that there is this very nice interconnection between irreducibility, which is a matrix property, and the associated digraph of the matrix. So the matrix, the digraph, which is obtained by taking the entries in the matrix as representing the existence of an arc or not. And we have that a matrix is irreducible if and only if the associated digraph is strongly connected. And if we have a stochastic matrix, a cool thing there, we have a stochastic matrix, so which has all its eigenvalues less than or equal to 1? Well, if we have irreducibility, then rho of A equals 1 is an eigenvalue, and it has, actually, this is not entirely correct. It doesn't necessarily have, yes, it has multiplicity 1. Sorry, it has multiplicity 1, but this is incorrect. It should be less than or equal here. I will, oh, my computer is right next door to this. So it's less than or equal to 1 here. Okay. So that's it. If you look at the digraph associated to a matrix, you can say whether it's irreducible or not. Now let's think about let's go back to the Markov chain. So I'll remind you that what we have is that in the Markov chain, P of n is equal to P of n minus 1, or times the transition matrix P. Or, if you want it the other way, P of n plus 1, probably I should write this, is equal to P of n times the transition matrix P. Okay. Where P of n and P of n plus 1 are row vectors. Okay. This is what we were describing before. Now, what happens to this probability vector? Well, if I suppose that I'm starting out with an initial distribution of probability, okay, so I write that P of 0 is actually P1 of 0, P2 of 0, down to PR of 0. So this is my initial distribution of probability. It is a probability vector, so the sum on I of the Pi of 0 equals 1. But I don't know. So for instance, it could be that we have 4 states. Well, remember, the example that we're going to come back with, the genetics example. In that genetic example, I haven't made that explicit right now yet, but we will have 3 possible states. We will have GG, we will have, so the dominant, we will have the hybrid, and we will have the recessive. So when I'm looking at this system for the genetics, I could start and say, well, I don't quite know what the distribution is, but, well, I mean, I don't quite know what it is, but I'm going to assume that there is a probability 1/3 that I'm in each of those. So I'm equally likely to be dominant, hybrid, or recessive. Okay? So that's one thing that we can think about, and that's how we set up the problem. We start with a hypothesis about the distribution, and then we wonder if I've assumed that that I had a probability 1/3 of having each one of these configurations, then what is the long-term behavior of the chain? And as I said, we'll come back to that very soon. But that's the underlying idea. So if we have that, then we're wondering how things evolve. Well, we have a rule. As I pointed out, what we have is a sequence. Okay? The Markov chain defines a sequence of iterations. So I can write exactly like I did when I was showing you the example of a sequence of scalars before. I can do the same. I can say, okay, P of 0 is my initial state. To get P1, I use the formula that I had just erased. I get that P of n plus 1 is equal to P of n times P. So P of 1 is equal to P of 0 times P. P of 2 is P of 1 times P by the iteration formula. But I have just written that P of 1 that I have here is actually P of 0 times P. So what I get is that P of 2 is P of 0 times the square of the matrix P. And I can continue. So for any n, what I'm going to find is that the probability distribution vector of the state of the system at time n is going to be the probability that I started with, probability vector that I started with, multiplied by the nth power of the matrix P. Okay. Now, if I want to know what happens to the chain in the long term, all I have to do is therefore to take the limit of Pn when n goes to infinity. I want to know, okay, what happens if I let the system evolve? What happens to it? Well, if I take this limit, it's the same limit as here. So the limit of Pn when n goes to infinity is the limit of this here. But P of 0 is given. Okay, it's not a function of n. I've given myself a P of 0 to start with, and I'm asking what is the overall outcome, and therefore I can simplify the expression and write that the limit when n goes to infinity of the probability vector is given by the value I started with times the limit of this power of the matrix. Of course, that limit has to exist. Okay? It's not just you don't know that it exists. Okay? A priori, you look at this thing, I don't know why, but I'm going to show you that in some cases we know exactly what happens. Now, we get back to this. We're saying, okay, the limit is P of 0 times the limit when P of n. Does that limit exist? Well, the first thing, and if you remember this was part of the worksheet for yesterday, is that if you have non-singular stochastic matrices, then the product is a stochastic matrix. And I'm not going to show you, well, I mean, I could really show you. It's quite simple. I'm actually, when I'm thinking about this, I'm not entirely sure that you need it to be non-singular, but let's just stick with non-singular. So if M and N are stochastic matrices, it means that M times the vector of ones is equal to the vector of ones. Okay, I'm going to assume that they're both stochastic by rows. So when I sum the row, I get a vector of ones. And n is the same. It's a stochastic matrix. I should indicate, so 1 here is just the vector with only ones. Column vector here. Okay. So what's Mn? Well, Mn is stochastic if when I take the sum of this, the row sums, I get 1. But m times n, so because n is stochastic, I get that this here is equal to 1. And because m is stochastic, this is equal to 1. Okay. So that means the product of row stochastic matrices is a row stochastic matrix. The product of column stochastic matrices is a column stochastic matrix. I'll just point out that if you take products of row and column stochastic, that was one of the questions in the worksheet, it's not so clear, of course. But if they have the same property both, it's easy to show. So that means that when we are looking at this power here, well, any power, any finite multiplication or infinite multiplication of that stochastic matrices is still going to be stochastic. So n to the k, or p to the n in this expression here, is a stochastic matrix. So that already tells us that it has nice properties. Okay, it's got 1 as an eigenvalue, blah, 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 blah. Everything that we've seen so far is true about it. And even further, remember this, this was another part of the worksheet that came up recently. Actually, the fact that the matrix is stochastic is even stronger than I'm using a vector that's a probability vector. It works with anything. A stochastic matrix is going to preserve the norm. So if you think about it this way, and I won't show it, but it's quite easy to show. Once again, you'll end up using this vector of ones. I'll let you work out how to do this. So if I define a sequence, so here I've taken the matrix to be column stochastic. Compared to what we're doing in the rest, just transpose, okay? But I take a column stochastic matrix, I take a column vector V, and I define the sequence. This time, instead of multiplying on the left the matrix, because I'm looking at a column vector, I'm multiplying it on the right. Okay? So I'm multiplying A by a column vector, and A has all its column sums equal to 1. Well, if I impose that in this sequence, the first entry has norm, so the sum of its elements I'm going to take here, the norm is equal to K, then this is going to be true for all subsequent terms. Okay. I shouldn't have written the norm this way. I should have written really as the sum of the entries, but it's actually going to be true for any norm. Okay. This tells me that, in particular, because I have this result, I can expect that when I'm taking my products with a stochastic vector, the result that I get is still a stochastic vector, which is important because, like, I'm dealing with probabilities. I don't want probabilities larger than 1 or anything like this. Okay. Now, one case where we know exactly what happens to that matrix P to the K, the limit of P to the K, is when we have a matrix that has, well, first of all, we have a Markov chain that has the property that it's what we call regular. So a Markov chain has pk, so the transition matrix, that is positive, not non-negative, positive, for some integer value k. You can find a value of k which is such that p to the k is entry-wise positive. So all the entries are positive. And the same way as we saw that there was an equivalence between a matrix being irreducible and the graph being strongly connected, we are going to see similar connections. But in terms of first the definition, this is the same definition as for what we call primitive matrices. So if we have a non-negative matrix, we say it's primitive if we can find an integer k such that n to the k is positive. So this is exactly saying the same thing as this, okay? For any matrix. The matrix doesn't have, here in this case, it doesn't have to be a stochastic matrix. Any non-negative matrix that has the property that there is a k such that n to the k is positive is called primitive. Okay. But in the case of Markov chains, we're dealing with matrices that are not only non-negative, but they're also stochastic. And therefore, we have this equivalency here that a Markov chain is regular if the transition matrix P of the Markov chain is primitive. Okay. Now, again, remember what happened with irreducibility. Irreducibility was complicated to characterize if you did not look at the graph, the associated graph. And here, this is going to be a bit the same. If I give you a random matrix, like random, I mean, like pick a non-negative matrix out of my head, I throw it here, and I say, is this matrix primitive? It can be difficult to conclude. We're going to see how to do that. Now, a primitive matrix, so this is the proper definition. Okay, I'll add a few extra tidbits of information as we go. So the matrix is primitive, as I already said, if there is a k When I write star like this, I mean without zero. So this is a positive integer, not a non-negative integer. So there is a positive integer k such that a to the k is positive. We call primitivity index the value of k, the smallest value of k for which this is true. Okay? Because once you have a to the k positive, if you multiply it by another matrix that's non-negative, you're going to remain positive. Okay? Actually, not all the time, but most of the time, this is what's going to happen. So the smallest value that gives you all the entries of the matrix positive is the index of primitivity. And we say that a matrix is imprimitive if it is not primitive. And I remind you that we saw this very briefly a bit earlier in the course when we were looking at the Perron-Frobenius theorem, which I gave you very, very quickly, but that was one of the possibilities. It was that the matrix was primitive. And that was the ideal situation in terms of concluding about where the eigenvalue were located. Now, this is something that's workable. That first theorem there, this is a sufficient condition for primitivity. And that sufficient condition is very simple. So if you have a non-negative matrix, that's irreducible. So remember, this takes us back to a few slides ago when we were saying a matrix is irreducible if the associated digraph is strongly connected. So suppose that I have a matrix that has an associated digraph that is strongly connected. So the matrix itself is irreducible. If there is one positive diagonal entry, then the matrix is primitive. And if you go back to what that means in terms of a digraph, having a positive diagonal entry means you have a loop. So you are allowing digraphs with loops. If you're allowing loops, then if you have a digraph and at least, so it's strongly connected, and one of the vertices has a loop, then you know that the corresponding adjacency matrix is a primitive matrix. Okay. And there's some very cool things that we're not going to play with very much here, but for those of you who deal a little bit more with this, you might end up seeing this in another life. The index of imprimitivity is essentially a number that D here, and we define it to be the number of eigenvalues that have the same modulus, lambda, as the spectral radius of the matrix. So remember, from the Perron-Frobenius theorem, we know that the spectral radius is an eigenvalue. Okay? Because we're in the primitive case, we know that this eigenvalue, we're not necessarily in the primitive case, but we're in the irreducible case, for instance. We know this eigenvalue has multiplicity 1. But there can be other eigenvalues on the disk, like on the periphery, so on the circle with radius rho of a. There can be other eigenvalues with the same modulus. They're just not equal to rho of a. And if we count how many eigenvalues are on the disk of radius rho of a, then this is that D that we get. And furthermore, so the D is the index of imprimitivity. So if the imprimitivity is 1, then the matrix is actually primitive. Okay? So if there's only one eigenvalue, and that is rho of a, that has the same modulus as rho of a, then the matrix is primitive. If there are more, the matrix is imprimitive. Okay? And that D is giving us this. And there is a very interesting connection with graphs, because look at what happens. That D, that index of imprimitivity, is the greatest common divisor of all the lengths of closed walks in the associated digraph. Okay, so I'll have an example for you. Oops, I skipped ahead. I'll have an example for you right here. And we've looked at this one already, but now I'm going to make it into a Markov chain. How do I do that? Well, I'm going to weight the arcs by the probability. Okay, so this here is, let me see if I can, this is P1, 2 equals 1. That means the probability of moving from 1 to 2 is 1. This here is P2, 3. And this here is P3, 1. And all the other entries are 0 because this is a stochastic matrix. So the column sums, the row sums have to be 1. And because I have a 1 already on each row, all the other entries have to be 0. Okay. So this simply says, going back into what this means, this simply says that the probability of moving from state 1 into state 2 is 1. The probability of moving from state 2 into state 3 is 1. This means these movements are obligatory. I have no choice. Okay? If the probability is 1, this means I always do it. So this is a chain where you're switching between states every single time. And we saw this graph already. I showed it to you, but not in the context of a Markov chain. So the transition matrix that is associated to this, if we consider this as the state transition graph of the Markov chain, well, it's simply this matrix that we have seen already. Okay. But now let's think about the length of closed walks in this graph. How long does it take me to go for the shortest length of closed walks? Okay. How long does it take me to go from 1 to 1? Well, I can start here, 1, 2, 3. From 2 to 2, I'm going to go 1, 2, 3. From 3 to 3, I'm going to go 1, 2, 3. So these closed walks have lengths 3, 3, and 3. So when I take their greatest common divisor, I get 3. So this matrix is imprimitive, with index of imprimitivity equals to 3. And this means, in particular, that it has 3 eigenvalues with modulus equal to the spectral radius. This is a stochastic matrix. The spectral radius is 1. So I'm going to have 3 eigenvalues with modulus 1. And in this case, it's a 3 by 3 matrix. This means all the eigenvalues of this matrix have modulus 1. I don't know what they are, except for the one that is at 1, 1. Okay? And that is at, the spectral radius. So the one that's equal to 1. But it's at 1, 0 in the complex plane. Now, let's add a loop. And from that theorem we saw before, this is a strongly connected graph. Okay, I can go from any vertex to any other vertex. And I have a diagonal entry that is non-zero. Actually, and here, by the way, so if I took, this is the Boolean representation of the transition matrix. The transition matrix itself has 1/2 and 1/2 here. But I can take the Boolean representation of this. Okay. And now, if I look at the shortest paths, closed paths, from 1 to 1, well, I can go like this. So this has length 1. So now I have 1, 3, and 3. What is the greatest common divisor? It's 1. The greatest common divisor of the length of the shortest paths is 1. This means the matrix is primitive. And that Markov chain is regular. What? Yes, very briefly, I'm not going to spend a lot of time on this. There's a few results. If you want to show primitivity, it's complicated. I'll I'll just point out, so first of all, there's this, this upper bound essentially for the power that is going to give you the index of primitivity. If we have a matrix and we know it's primitive, then we know that the k value, so the index of primitivity, that is going to give us primitivity, is going to be some number between 0, 1, and n minus 1 times n to the n. This is humongous. I mean, this is a very bad bound, but it's a bound. If we have, and this is back into the graph domain here, if we have a primitive matrix and that we have that the shortest simple directed cycle walk in G of A has length S, then we know that the primitivity index is less than or equal to n plus S times n minus 1. This is much better than this one. Okay, the n to the n here is enormous. Here we are essentially at the maximum in n squared. This is better. This is another one that you can try. If you have a good algorithm for raising powers to a matrix, you can just check that this matrix is positive or not. If this matrix is not positive, then you know that the matrix is not primitive. And this, again, takes us to what I was just talking about. If we have an irreducible matrix and it has d positive entries, so it's an n by n matrix, and on the main diagonal, you have d of the entries that are positive, then the primitivity index is less than 2n minus d minus 1. Okay. This is just, like, sometimes it might be useful to some of you. Now, this is where it becomes really important. So suppose I have a Markov chain, and that Markov chain is regular. In other words, the transition matrix P is primitive. Then we have the following. The powers of P, when you take n to infinity, they approach a stochastic matrix W. So there's a limit. What that means is that there is a limit when n goes to infinity of P to the n, and that limit is this matrix W. Okay. Each row in the matrix W is the same vector, and it's a stochastic matrix. So each row is a stochastic vector, okay? And the rows are the same, and the components are positive. They're not, you know, like, it's not going to be 0 somewhere and the rest sum to 1. We know that all the components are positive. So that means that if we have a regular Markov chain, we can find that the limit when n goes to infinity of P of n is simply P of 0 times this matrix. And I'm going to show you how to compute this. To compute W, we first make the following reasoning, which is something that you will see from time to time in a variety of contexts in math. So this is that we're saying, okay, when n goes to infinity, there is a limit. So the process converges. But that process, it is defined by this recurrence equation here. Okay? P of n plus 1 is equal to P of n times P. But if I have reached my limit, then P of n is equal to W. Okay? It's the W that makes up this matrix. Remember I said, like the matrix, it's this theorem here, remember that the matrix W consists in rows that are all the same. So I'm going to extract one of those rows, and that is going to be what we call a fixed point. Okay, and the fixed point equation typically takes the following form, which is very, very common. It is W times P equals W. What did I do here? Actually, I should have written it the other way. I should have written it as W is equal to W times P. All this is saying is P has reached this limit that I know to exist. And therefore, I can replace P of n and P of n plus 1 because I've reached the limit. So things are not changing anymore. Okay, I'm at the limit. Things are not changing. So P of n is equal to P of n minus plus 1 is equal to P of n plus 2, etc. They're all equal to the limit. So I replace P of n by W, and I solve this. But what is this? This is W times P equals W. That means this is, so W being a row vector, okay? This is a left eigenvector equation for P. What this is saying is the solution to my fixed point is a left eigenvector corresponding, of course, to the eigenvalue 1, because here what is missing is lambda. So the lambda that I have here is 1. So we already know, because P is a stochastic matrix, we know that P1 is 1. This equation here is the eigenvector equation for the right eigenvector 1 associated to P, to the eigenvalue 1. And now what we're saying is, well, our limit is actually going to come as the left eigenvector, W. So I could think of, if we use the notation of vectors in columns, that would be with a T, okay? But here, remember that I'm looking at vectors as being row vectors. So this one is now the, so this is right, and this is left eigenvector. Okay? So that's how I find my limit. It's quite simple. I have a matrix, my transition matrix, and all I need to do is find the left eigenvector of this. And I will just point out that if, and I've said that before, but I'm repeating it here, if your solver doesn't know how to do left eigenvectors, well, the left eigenvector is simply the right eigenvector of the transpose. Okay. So I compute this eigenvector. Once I have it, I check that it has norm, norm in terms of that norm here. Okay, the sum of the entries must be 1 because it is a probability vector. So if I find a result, and you have seen now, you've played with eigenvalues, eigenvectors enough in this course that you know that very often the numerical solution will not satisfy what you want. You might actually pull out an eigenvector that has all its entries negative, but it doesn't matter. What you're doing now is you say, okay, if it's all negative, let me all make them positive, and then let me divide by the sum. This way I get a vector that has norm 1. Well, that norm 1. Okay? So, this was a rather lengthy tour into the theory behind this. And let's go back to the genetics example. So, remember that, well, I just talked about it a few minutes ago, so it should be clear, it should be fresh in your minds. We're considering this system which has 3 possible states. You're either dominant, recessive, or hybrid. And now I'm going to consider an experiment. I'm going to run an experiment to see the effect of this Mendelian inheritance. And the way I'm going to design my experiment is going to be very simple. I want to know what it's like to have hybrids. So what I'm going to do is I'm going to use continued mating. So suppose this is an insect population or something like this, which reproduces quickly and you can control. You'd use a process of continued or continuous mating. Okay, you start with an individual that has either you know what it is, and in that case it's good. So for example, I would say, oh, that one is hybrid, or I say this one is dominant. I don't know, or I just say I don't quite know what's in there, and I would like to know what it does. And I'm going to mate it with a hybrid every single time. So I take an individual at random. It might be of known type or it might not be of known type. But what happens is that every time I pick an individual, I mate it with a hybrid. So every single time I put a hybrid in there. And I'm supposing that, of course, I need offspring to be able to carry out this experiment. And then what's going to happen is I have one or many, probably in the case of insect populations, for example, it's probably many. I have many offspring, so children, and I pick one of these offspring at random, and once again, I mate that offspring with a hybrid. And I'm going to repeat this. I repeat and repeat and repeat. And the question is, well, what's my population like if I keep on doing this every single time? Every single time I get a bunch of insects, I pick one at random, mate it with a hybrid, look at the corresponding kids. When I get kids, pick one at random, mate it with a hybrid, repeat, repeat. So what we get is a Markov chain. And that Markov chain has three states, exactly what we were discussing before. I could have hybrids, dominant or recessive. Okay. So what happens? Well, I'm looking at, and remember we way back when we looked at what happens when we mate things when we have a parent that's a hybrid. So we have three states, which are indicated here. And I'm going to write the name of the states, okay, because it's clearer if I say GG rather than S1. The second state is hybrid. And the third state is recessive. And what I say is, okay, I'm going to pick one of those guys at random, and I'm going to see what happens when I mate them. And so you have to go back to when we computed the probability. So here the idea is what happens. So if you go back, let me go back. These were the things. So remember that we considered what happens when you have, that's exactly the situation that we're looking at here. So if I'm here, remember this is one of the situations. So here I've picked this one up. I didn't know that, okay? But when I picked up an individual, I picked up a capital GG. And remember that every time I'm throwing in a hybrid. So that means my other parent is automatically little g, capital G, little g. And so these are the possible outcomes, okay? So in that case, if I mate those with a hybrid, what I see is that I can have a probability 1/2 of remaining dominant, or with probability 1/2, I'm going to become a hybrid. Okay. The other possibility is in my selection process, instead of picking up a dominant, as I was just saying, I've picked up a hybrid, which is the next one here. So if I've picked up a hybrid because I'm mating with a hybrid, this means my two parents are hybrid. And therefore, the possible outcomes here are I have a probability 1/4 of being dominant. I have a probability 1/2 that my kids are hybrid, and I have a probability 1/4 that they are recessive. Okay. Finally, instead of picking a dominant or a hybrid, I picked up an offspring that was recessive, and I mated with a hybrid parent. Then the possible outcomes are here, and the probabilities of transitions are the ones indicated here. I have a probability 1/2 of moving here back into hybrid, or a probability 1/2 of remaining recessive. And this is my Markov chain when I have continuous mating with hybrid parents. Okay, these are the probabilities that I will make those transitions with a parent. And this gives us this matrix that we have here. Okay, the probability of moving from GG into GG is 1/2, into hybrid is 1/2. Okay, 1/2, 1/2. The probability of moving from hybrid into dominant is 1/4. The probability of remaining hybrid is 1/2, and the probability of becoming recessive is 1/4. Okay, so that's that second row in this matrix. And finally, if I'm here, my probability of remaining, of moving back to hybrid is 1/2, and my probability of remaining recessive is 1/2. And so my transition matrix is this guy here. A regular Markov chain. Let's use the theorems we just saw. That graph is clearly strongly connected. Okay, if I take any of those 3 vertices, I can go to any of the other vertices by following the arrows. And from the sufficient condition for primitivity that we saw, we have loops. We actually have not only one loop, we have 3 loops. So we have 3 loops, so the matrix is primitive. The matrix is primitive means the Markov chain is regular. And we can use the previous theorem to determine where we're going. Okay? And actually, the index of primitivity is 2. If we take this matrix and we take its second power, it's all positive. Okay, so, but we could also justify it the other way. Okay. So P is primitive, the Markov chain is regular. That is saying exactly what I was. I don't know why I put this theorem again, because we have it before. Okay, so I'll remove that one. It's an application of this theorem otherwise. And here this is the same graph as otherwise as over there. This is the transition graph with the probabilities. Yes, it looks good. Now let's compute the eigenvector, left eigenvector, associated to the eigenvalue 1. So we write that W1, W2, W3, the components of that eigenvector, times the matrix, must be equal to W1, W2, W3. That gives us this system of equations. We do some stuff, and we get this vector here. Okay. So this is the limit of the chain, well, not the limit of the chain. This is the vector that if you multiply by P0, you get the distribution because it depends where you started, okay? But this is the W that makes up the matrix, and the matrix W, capital W, is just this vector repeated 3 times. Now I'm going to I have a few minutes. I don't know if I'll be able to do everything today. I hope to be able to do everything today. We'll see. If not, there will be a few minutes left in the next lecture, but really almost nothing. Now I'm going to change this experiment that I was doing, And what I'm going to do is that instead of mating each generation with a hybrid, every time I'm going to introduce, so I'm picking at random, still the same process. I pick up an offspring, I mate that offspring at random with an individual, but instead of choosing that individual of known type to be hybrid, like in the previous case, I'm going to take that individual to be dominant, okay? Capital G, capital G. So every time, pick up an offspring, mate it with a capital G, get offsprings, get a new offspring, mate it with capital G, etc. So the graph now changes, okay? And what you get is this graph that is shown here. I'll let you go back. It's quite easy to derive it, okay? So if you go back the same way as before to these possibilities we enumerated, but now you consider that each time what's happening is that you have a capital G individual instead of a lowercase g, capital G individual, and then you look at the outcomes. And so what you get is the transition graph here. Okay? It's still as annoying to erase this stupid thing. And yes. Okay, so the graph is the following. So what you are going to do is, remember, you're mating with capital G. And if you recall, when we have two parents that are capital G, so two parents that are dominant, of course the outcome can only be dominant. If, on the other hand, you've picked a hybrid, well, with probability 1/2, it remains a hybrid, or with probability 1/2, it becomes dominant. And if you've picked a recessive, then with probability 1, you can, because I'm mating it with capital G, I'm always going to pick up a hybrid, okay? Because either I donate one of my left capital G, let's say, and my right little g, or I donate my right capital G and my left little g. In both cases, I end up with a hybrid. So that means that if I'm here, I can't stay there. With probability 1, I'm moving here. If I'm here, I'm moving here with probability 1/2, or staying here with probability 1/2. And once I've made it to the dominant case, I'm stuck there, okay? I have, with probability 1, I'm staying in the dominant case. So my transition matrix is much simpler than before. Okay, you can see I have from 1 being capital G, I can only go to capital G. From 2, I can go with probability 1/2 here, and probability 1/2, I remain in the same place. And with 3, I can only go to 2. So I leave little g after one iteration, and I can never go back. I leave hybrid. Whenever I do, it's done, okay? I cannot go back. And when I get to capital G, I'm stuck there, and that's the end of my journey. Whatever I do from now on, I'm always going to make dominance. Okay. This is a different type of Markov chain, which is also very, very interesting. And it's what's called an absorbing Markov chain. And looking at the time, I think what I will do is I will give you the definition in this lecture, then I will cut, and I will make the remaining little piece. Actually, let me stop here. Let me go back to this and stop at this point in the lecture, and then the next lecture will be absorbing chain.